Today we are diving into the breathing core, a master class on deadman, fluid dynamics, and hearth longevity. This image shows the vibrant, high temperature heart of our furnace, where mastering the flow is not just a technical goal, just accomplish the tapping and everything. It is not the goal. It's the key to the furnace entire campaign life. So by end of this session, you will understand why we treat the heart as a living, breathing system. So let's start by challenging how we used to think about this process. We need to move away from the old way of looking at the heart. In the old paradigm, we treated the heart like a static bucket. So where only quality of the brick mattered. But the reality is that the dead man is an active and dynamic matrix. So it is active as well as the dynamic also. So it's a semi-stagnant, actively renewing column of coke submerged in liquid iron and slag, controlling the mechanical, thermal, and fluid forces here directly dictate how many years of life we get out of the furnace. And to control those forces, we first have to understand the physics at play. So let us see a battle of forces. How looks like. So we have the downward vector, the weight of the solid body and the drag of the ascending gases. Opposing that is Archimedes' buoyancy, where the high density liquid iron exert a massive lifting force. The key insight here is that the vertical position of the dead man is constantly shifting as liquid level rise and fall. This shifting is not random. It follows a very specific cycle. So what is that breathing cycle? So in this slide, we will see the breathing cycle. What does it a healthy heart look like? It looks like these four stage cycle. What are those? So step one as it's shown. First the heart fills and the buoyancy forces increases. Coming to a step two, the core float creating a transient coke free zone at the bottom. Coming to the point 3, then we tap the furnace, liquid drains and pressure is relieved. And finally coming to the point 4, the dead men settle back down, grinding and renewing the boundary layer. So this continuous mechanism migration is what prevents long-term stagnation. So such type of stagnation is very rare. Now if this cycle break, we end up in one of the two dangerous extreme and and this what is shown in which sitting versus floating state is shown. This table is your diagnostic guide. It gives a full briefing for the two extreme. A sitting dead man rest on the floor forcing liquid outward in the gutter flow, which leads to elephant foot erosion on the sidewall. On the flip side, a floating dead man creates a coke-free zone at the bottom, leading to central underflow and bowl-shaped erosion at the center bottom. Both states create high thermal stresses, just in different places. So let's look closer at why sitting state is so dangerous for the sidewall. So what is the erosion threat? This is all related to erosion threat, sitting or floating. And with respect to this erosion threat, its intensity, nature, we have to prefer what type of sitting or floating is beneficial for the furnace campaign. So when the core loses permeability, perhaps it's a clog with the fines, central flow is choked, as it is shown by these red arrows. So the liquid iron is forced into high velocity peripheral movement around the outer edge. Now this result in accelerated heat transfer and severe mechanical frictions, mechanical force, and this is the direct path to catastrophic elephant foot erosion. But floating too much is not is the answer either. So the stagnation threat. If the dead man float excessively, it creates an oversized passage adherence. This unrestricted central flow causes central scouring or grinding away the middle of the hearth bottom. Conversely, if the flow bypasses the packing layer entirely, we risk thermal stagnation leading to a cold hearth and the buildup of a massive, massive, unmanageable salamander. So, how do we find the middle ground? So, our goal is not a single static state. There is not a single static state. We want the uh, Goldilocks zone, control dynamic breathing. The dead man must periodically lift for cleaning and flow, then settle to maintain thermal contact and renew the Koch matrix. So this is an active fluid dynamic challenge, not just a material science problem. So to stay in that zone, we need to see what's happening inside. How do we see the unseen? We use a digital twin powered by three data streams. Electrical EMF sensor map the isotherm and deadman shift. Mechanical strain gauges track shell expansion to calculate liquid level. And third is the thermocouples feed inverse problem wear model. These data transform the job of a operator. Now coming to the real time monitoring means we no longer rely on the guesswork or looking at the tafel splashing. We can track deadman dynamics versus hot blast volume using strain gauges, LLMs and EMF's pattern recognition. we can instantly detect if the dead man has shifted or if a scaffold has broken down, allowing us to decide exactly when to open or close a cast. We can even look down to the microscopic level also. Now we use CFD DEM coupling to track the deadman cleanliness index or DCI. This measures the actual carbon content of tapped metal versus theoretical saturation to see if the core is clogging. We have learned that while core reasons take week to dissolve, it takes a long time. Flow channels near taphole renew in just a day. So maintaining a void edge of zero point 0.3 to zero point 0.5 is critical to prevent iron from being violently forced into the walls. So now let's look at the actual strategy we use to manage this. So intelligent tapping, our first tool is the gap time management. By adjusting the time between the casts, we control peak boundary of buoyancy, giving the health just enough time to breathe. So without floating out of control. So we also match the drill bit diameter to desired flow out coefficient and use LLM system to decide whether to interrupt a cast during the gas burst to stabilize pressure. So beyond timing, we also look at the physical geometry of the taphole. So a short taphole is a major risk. It allows high peripheral shear and head load on the side wall. The long taphole imperative physically bypass the gutter, forcing liquid to bend inward towards the center. Additionally, a deeper sum provide the volumetric buffer needed to ensure Archimedes' buoyancy can actually lift the dead man. Finally, we manage the dead man from the top of the furnace. So coming to the core uh, permeability, the integrity of dead man start at furnace top with the center coke charging. By charging large high quality coke into the center, we ensure it survives the descent to the hearth. This flushes out fines and improves our DCI. If the hearth cools, we immediately adjust blast momentum and the center coke ratio to physically warm up and flush the core. So let's bring all this together. So in conclusion, we can summarize or we to summarize refractory longevity is no longer just a uh, uh, just a material problem. It is an active real-time fluid dynamics challenge. By triangulating EMF, strain, and thermal data, we make the invisible core visible. By executing precise tapping, uh, tap hole, and charging strategy, we maintain that dynamic breathing that ensures stability, efficiency, and a maximum campaign life.